Hi class, in this lecture I would like to talk about how to use sensitivity analysis on LP. So key of this lesson is to know what is the sensitivity analysis. Sensitivity analysis, or we will call it post-optimum analysis, is used to determine how the optimum solution is affected by changes. There are two parts that will affect the optimal solution. The first one is the objective function coefficient, and the second one is the right-hand side values. There are two general forms of LP. One is for minimization problem, and one is for maximization problem. So we consider the coefficient in the objective function like C1, C2, and Cn. And for maximization here is B1, B2, and Bn. The right-hand side means the sign on the right of the constraint, like B1 here and C1 to Cn here. So why we need sensitivity analysis? Because it is very important for decision maker to operate in a dynamic environment with imprecise estimate of coefficient. Remember that when we build the LP model, we need to determine index and the parameter. So for the parameter, we need to analyze in advance so that this value will affect our final decision. So when there exists imprecise of the parameters, normally your final decision will have some uncertainty effect, so that the optimal solution will also imprecise as well. So sensitivity allows a decision maker to perform what-if scenario. So we can change the coefficient a little bit to see if we change a little bit value, then our optimal will be changed or not. Or if we increase the requirement or resources, then what will happen for our final decision? We start from the objective function coefficients. We can use this example. Maximize z equals to 10 times x1 plus 9 times x2, subject to 3 constraints. If we use the graphical representation of this model, we can see the right-hand side of this slide here. The final optimum solution is x1 equals to 540 and x2 is 252. Okay, then there is a line here and line here for two constraints, and we can see if the slope line of the objective between this region, then finally the optimal solution will not change. Okay, so the range of optimality for each coefficient provides the range of the value over which the current solution will remain optimal. Is the purpose for the objective function coefficient analysis. Okay, so how can we calculate the range for the slope? We start from the objective function. We assume that the coefficient of the x1 is c1, coefficient x2 is c2. Okay, and then we assume if the we let the c2 set to be 9. Okay, then we can change a little bit from the objective function to this line equation, and we will find the slope for x1 here is minus c1 divided by c2. Okay, then the slope will between the two constraint here is minus 3 over 2 and minus 7 over 10 here. So C1 divided by 9 minus the value will between the minus 1.5 and the minus 0.7, okay, here. So finally, we can find the value of C1 is between the 6.3 and the 13.5. Okay, so that means if we are setting C2 equals to 9, then the C1 will between the range from 6.3 to 13.5. And between this value, we will know the optimal solution will not change. Okay. And also, we can set in if we can try to make the C1 increase to the 13, okay, and C2 reduce to 8, okay. In this example, we will find the range for the C1 and C2 will be into here. Okay, so we can make some scenario if we change the coefficient of C1 and C2, might be the optimum solution will be changed and the optimum value will be also changed. Okay, so that's the meaning that scenario analysis or sensitivity analysis will provide decision maker to do the scenario analysis to know what if we do what, if something happen, then what will happen. The second part, we will try to do the value change in the right hand side. So how a change in the right hand side for a constraint might affect feasible region and perhaps cause a change in optimum solution as well. The change in the value of optimum solution per unit increase in the right hand side of the constraint is called the dual value. Normally, for any kind of solver like Excel solver, or you can use the games with simplex solver, when you solve the model, it will provide the dual value for each constraint and dual value for the variable. Then you can see the solution report and find the dual value. As the right hand side increase, other constraint will become binding and limit the change in the value of the objective function. So now you will know these two parts of scenario analysis is very critical to our analysis. Otherwise, sometimes when you have imprecise parameter, then you will do the wrong decision. Okay, let's see the same example for this. The original model, the first constraint, the right hand side is 630, but now we try to increase 10 units. And we can redo and resolve the model. Then you will find the new solution will 527.5 and the x2 is 270.75 will be the solution. Okay, and the new objective value is here 7,711.75. The original one is 7,668. Then we will find if we increase 10 units of the right hand side, which will cause the objective value increase 43.75. And then because the definition of the dual value is we increase the 1 unit of the right hand side, the change of the objective value, so we will divide it the difference between these two objectives by 10, then we will find the value here is 4.375. Okay, so that's the dual value for the first constraint. And if you decrease, the objective will also decrease for the same value, 4.375. And we can go to the games to see if we can find the value. In order for the time limitation of the lecture, so I already put the model in the games. Okay, and then we can do it. Okay, and we go to the solution equation here. So here you can see the number of the first equation here is 4.375. That's the results, which is exactly the same for our calculation. And also you can do this by, for example, this is original objective value here is 7,668, right? Then you change your model here, the right hand side from 630 to to 31. Okay, then you run again. Then you will have this value. Okay, 7. I write down it. It's very difficult. Here we write down is 7672.375 and the minus the original. So I run again for the original model. Okay, which is 7668. Then this number will be exactly the same for 4.375, right? Okay, so actually you can direct find the dual value from your report. Okay, so I already give you the games code, and you just copy and paste the code, and you can do some experiments by yourself. Okay, so we can also find some dual value for variable, which means the reduced cost. Okay, it's the same. You can just check the solution report for solution value here, and go to the low level upper and the dual value there. Okay, without any value means 0 in games report. Okay, so reduced cost is 0 here, which you can look the marginal value for the variable. And now, how can we determine the range for the right hand side change that without any change of the objective value? Okay, so the way is that you go to the solution report and go to the equation. Okay, and you can see the solution. Okay, might be. I think should be solution equation. Sorry, here. Okay, and you will find the equation 3 here, and there are upper bounds, okay, and label. Label means now we only use the 170 units resource, but we still have a room to change to 135. So in total, we have around the value have 18 changes. Okay, have 18 changes. So this one is the around change for the constraint 3. So if you try to find a range for all allowable increase or decrease, basically you can do the experiment and try a lot of times and determine the value, but it is really troublesome because you need to maybe do the infinite experiments. Then it's so time consuming. So some software report will provide you the whole table for the allowable increase or allowable decrease, so that you change the value will not influence the objective value. But for the games, the report is not complete. So you can use the Excel solver to get the answers. Okay, I try to put the model into the Excel and show the results. Now I will bring you step by step to construct this model and to find the sensitivity results for your model. Here is in Chinese, but I already changed the column's name, so you will know the meaning of the column. Okay. So we go to the Excel. The first one, we need to build this model. So we have two variables, so we just give the name for x1 and x2. The initial value, we always start from 0. Actually, you can start from any number for your initial value. But 0 and 0, which is actually is the feasible solution for this model, because all decision we start from the value 0. So we just set the value to 0, and we have objective and first constraint, second constraint, third constraint. We have 3 constraints, and here the CO here we need put the coefficient for objective function and coefficient of constraint. So we put here is 10 and 9 for objective functions coefficients, and the first one is 0.7 and 1, and the second constraint is 1 2/3, and third constraint is 0.1 and 0.25. Okay, and we need to calculate. Okay, we need to calculate objective value at this stage. Okay, so the equation here is, for example, if you want to calculate the objective value, you use the CO B3 times CO B2 plus CO C3 times C2. Okay, but because it already has a very good structure layout, so you just use the sum product function and then use the copy paste for save time. So I use the sum product. Okay, the first array is B2 times C2, then the second array is B3 to C3. Okay, And because the this seal B2 and C2 should be fixed, okay? Because we calculate the constraint value for the B4 and C4, we still need to times B2 to C2, right? So the B2 we put dollars, C2 put dollars to fix the variable array, and we just use the copy paste. Then you can get the constraint value for constraint 1 to constraint 3. Then we put the less and equal sign, just to remind us the sign, and then we need added resource value for each constraint. The first one is 630, and the second number is 708, and the third value is 135. Okay, once you finish your Excel model, then you go to the Excel solver and put all the parameters into the setting, then solve it. Then you can get the sensitivity table. If you don't have solver, you need to go to the option of the Excel and go to the add-in. Okay, and there is Excel solver here. Sorry for the Chinese character, but it means Excel solver. Then you execute, put excuse here and press OK. Then you can add the solver add-in into your Excel and go to the data tab. You can find the Excel solver here. I already make a video for you in the maybe week 1 or week 2. So if you are still not familiar with Excel, then you can go back to see the lecture video. Okay, then first one we need to set the objective. Then we clicked here and choose the objective value seal. In this case is E3. Okay, then press enter, and we need to set objective direction, which is maximize. Okay, and then we need to choose the decision variable, which is B2 to C2, and then we need to edit constraint. Okay, the constraint from E4 to E6, and the resource value is from G4 to G6. Okay, then press OK, and then we choose the solve method is simplex LP. Okay, then we solve it, and then now there are 3 reports here. Sorry for Chinese character, which means analysis results and the sensitivity analysis and the limits. Okay, then we choose the sensitivity reports and we clicked OK. Then you will find in the original table the x1 value is 440 and x2 is 252, which is exactly the same in the slides. And we go to the sensitivity report, and you will see all of the value here. For example, we have the constraint 3 here, right? Constraint here 3 here is 18, which means the allowable decrease for the constraint 3. Okay, so let's today's lecture talk about what is sensitivity analysis, which is related to we change the coefficient of the objective value and we change the right hand side of the constraint so that the objective value will not be changed. Sensitivity analysis also provides a decision maker for what if scenario because of the imprecise parameter. So hope you can use this concept for your application. At least you need to maybe carry out some sensitivity analysis for your final class project. Okay, so see you in next lecture. Bye bye.